Hello, my name is Leyva-Acosta and I am going to talk about information exchange in the Russian cards problem, which is a joint work with Eduardo Pascual-Aseff and Sergio Rajsbaum. The more general scenario for the Russian cards problem is the following. We have three players, A, B, and C, which we call respectively Alice, Bob, and Cath, and a deck of n cards labeled from 0 to n-1. A particular problem instance is determined by the signature a+b+c and the value of n, meaning that the cards from the deck are dealt to the players so that Alice gets A cards, Bob gets B cards, Cath gets C cards, and possibly R cards are not dealt to any player, so that n is equal to A plus B plus C plus R. Then, a particular deal consists of the hands of cards that each player gets, denoted with the italic letters A, B, and C for the hands of Alice, Bob, and Cath respectively. In this setting, Alice and Bob must communicate with each other via public announcements, and under the assumption that the deck composition, the signature of the deal, and the communication protocol are common knowledge among the players. It is also assumed that the communication starts with Alice's announcement. In the classic Russian cards problem, communication between Alice and Bob is required to be informative, which means that the protocol must allow Alice and Bob to learn each other's hand. Additionally, the protocol must be safe, also called weak one secure, meaning that Cath is not allowed to learn any card from Alice or Bob's hand. Recently, Rajsbaum considered the notion of minimal informative solutions for the problem. For this problem variant, we do not require for Alice and Bob to learn each other's entire hand, but instead we require the protocol not to be trivial, in the sense that Alice and Bob must learn something about each other's hand. In this work, the author keeps the original security requirement of weak one security, as stated previously. Most solutions for the classic problem have the form of two-step protocols, consisting of two steps or announcements, one by Alice and the other from Bob, determined by functions PA and PB respectively. Then, PA is defined on the set of possible hands that Alice can get, which are all subsets of size A out of the deck, so that the set MA is the set of possible messages or encodings for Alice's announcement. Similarly, PB determines Bob's message as a function of his hand and Alice's message. A special kind of two-step protocol are those in which Bob's announcement protocol, PB, is only a function of Bob's hand, so that the message he sends does not depend on Alice's message, and therefore they can both make their announcement simultaneously. We will say PA is an M-message protocol whenever the amount of different messages that Alice can send according to PA is M. When a player sends a message M, it becomes public knowledge that the player holds a hand in a specific set, denoted as in the slide, consisting of all hands for which the announcement protocol associates the message M. Following terminology from previous work, we call this set the announcement corresponding to the message M. The 331 instance with 7 cards of the generalized problem appeared at the Moscow Mathematics Olympiad in 2000, and this was later called the Russian cards problem. There are known solutions for this problem instance in which Alice can use a 6 or 7 message announcement protocol, which is informative and also safe. Since then, informative solutions for various instances of the generalized problem have been reported, for scenarios where all cards of the deck are dealt to the players. Some of these instances are shown in the slide. Some authors have even considered alternative requirements to those of the classic problem, such as stronger security formulations, as well as multi-party variants of the problem. Additionally, there are known impossibility results, such as the impossibility of an informative announcement when C is greater or equal to A minus 1, and it is also known that an informative and simultaneously safe announcement protocol does not exist if C is greater or equal to B. A well-known informative and safe announcement protocol for the classic Russian cars problem is one by which Alice announces the sum of her cars modulo 7. Then, this is a 7-message protocol that can be described as a collection of announcements as shown in the slides, meaning that the message M is associated with the set of all hands such that the sum of their cars modulo 7 is M. Notice that for describing this protocol, as we will do in the following, we omit the comma separating the elements in the sets of cards representing a hand, so that, for example, 0, 1, 6 represents the set of cards 0, 1, and 6. For illustration purposes, assume that Alice's message according to this protocol is 2 and Bob's hand is 0, 1, 6. Then it is clear that Bob would learn Alice's hand to be 2, 3, 4. Moreover, for the same message, if we assume that Cath holds the card 3, then she would not be able to tell with certainty a single card from Alice or Bob's hand, given that for any card she does not hold, she considers possible for Alice to have it, and also the opposite. For getting a formal definition of what an informative and minimal informative announcement protocol for Alice is, we could consider representing indistinguishability for Bob. In particular, for every hand B that Bob could hold, we could consider the set of hands that Alice might hold initially, this is before any announcement, given that Bob holds B. Then, this set consists of all subsets of size A out of the deck D, which are disjoint from B. Hence, for any two hands in this set, the scenarios where Alice holds one or the other are initially indistinguishable for Bob. Then, we could summarize this information via an indistinguishability graph for Bob such that the vertices are all possible hands that Alice could get and two vertices are adjacent whenever there is a possible hand for Bob disjoint from both of them. Then, this characteristic graph turns out to be the distant C+R Johnson graph for parameters n and a. Then, an announcement protocol for Alice can be seen as a coloring function for the distant C+R Johnson graph, so that the messages of the protocol are colors and color classes are announcements. Now, it is clear that for an announcement protocol PA to be informative, it needs to be a proper coloring of the distance plus R Johnson graph for parameters n and a, which means that for every possible hand that Bob could get, he would be able to tell Alice's hand after her announcement. This means that the amount of possible messages for an informative announcement protocol is at least the chromatic number of the distance C plus R Johnson graph for parameters n and a. Alternatively, for PA to be minimal informative, we only need that for every possible hand B for Bob, there are at least two hands possible for Alice given that Bob holds B, which are differently colored by PA. In particular, for problem instances where C plus R is equal to 1, it was shown that a minimal informative announcement protocol for Alice allows Bob to learn with certainty at least one card from Alice's hand. Now, it is clear that a two-step protocol PA-PB for a problem instance ABC, such that Bob's message according to PB does not depend on Alice's message, will be informative if PA is informative for this problem instance and PB is informative for the symmetric problem instance, which means that Bob's announcement is informative for Alice. Similarly, for a two-step protocol PA-PB to be minimal informative, we need PA to be minimal informative for Bob and PB minimal informative for Alice. For a two-step protocol to be safe, we need Cath not to be able to learn any card from Alice's hand or Bob's hand. However, she could learn some of the remaining R cards. Now, let's talk about the main contributions of our paper. First, we provide a two-message minimal informative protocol construction for the Russian cards problem, with signature 331 for a total of 7 cards. This construction is based on Singer sets, also called perfect difference sets, and yields a minimal informative and safe announcement protocol for Alice. For this construction, first we need a perfect difference set of size 3, which we call S. In particular, this could be the set with elements 0, 1, and 3, given that, as it is shown in the table, the differences modulo 7 of all pairs of distinct elements from the set are all integers between 1 and 6. Additionally, for this construction, we need another 3 set of cards disjoint from S. Let's say such set consists of the cards 2, 4, and 6. Then we construct a set of all hands of size 3, which are increments modulo 7 of the set 0, 1, 3, and the set of all those hands which are increments modulo 7 of 2, 4, 6. Then, the resulting announcement protocol for Alice consists in sending a single bit message that depends on whether her hand is in either of the sets previously constructed or in neither of them. As a preliminary result, we proved the lemma that is shown in the slides, and then we got one of our main results stating that the protocol CS resulting from the previously described construction is a minimal informative announcement protocol for Alice in the classic Russian cards problem. Additionally, we proved that for problem instances where C plus R is equal to 1 and B is at least 2, any two-message minimal informative protocol is also safe. This directly implies that the construction we previously presented does not only yield a minimal informative protocol for the Russian cards problem, but additionally a safe one. Moreover, we also proved that this same protocol CS resulting from the previous construction can be used in a symmetric fashion by Bob, so that we get a two-step minimal informative and safe protocol for the Russian card problem by which Alice and Bob need only to exchange a single bit, allowing them to learn at least one card from each other's hand, while Cath does not. Finally, we also considered informative solutions for the classic Russian cards problem, in particular six-message protocols. These are especially important since they are optimal in terms of communication complexity, given that the chromatic number of the Johnson graph for parameters 7 and 3 is known to be 6. The six-message informative and safe protocol showed in the slides was presented by Swanson and Stinson in 2014, and unlike the 7-message solution that we presented before, for this protocol the size distribution for the announcement or color classes is not uniform, since we have announcements of different sizes. Namely, 3 announcements are of size 5, 1 announcement is of size 6, and 2 announcements of size 7. Then our last result is that, other than this size distribution for the announcements, no other exists for a six-message solution for the Russian cards problem. As final remarks, we have presented the first minimal informative solution for the classic Russian cards problem, which allows both Alice and Bob to learn a card from each other's hands by exchanging a single bit. We also have shown that any two-message minimal informative protocol for instances where C plus R is equal to 1 and B is at least 2 is also a safe protocol. Moreover, we have shown that there is no six-message solution for the Russian cards problem with a size distribution for the announcements other than 555, 677. Now, regarding open problems, it is well known and easy to see that a solution for the classic Russian cars problem implies a solution to the problem of unconditionally secure secret key exchange. However, still remains the question of whether the minimal informative variant of the Russian cars problem could also lead to unconditionally secure implementations of some general-purpose cryptographic primitives, and in which scenarios. Moreover, a full characterization of the deals for which informative and minimal informative solutions exist is yet to be reported, since known solutions are limited to only few instances of the generalized problem. The further study of two-message protocols would be particularly interesting since such protocols are optimal in terms of communication complexity. Additionally, in future studies regarding minimal informative protocols, we could also consider a stronger form of the security requirement, such as perfect security. Well, we have come to the end of the talk. Thanks for your attention.